Good afternoon, everyone. So this is Advanced Thermodynamics and Combustion course. As we all know, being conducted under the NPTEL program, and today is the 12th uh, tutorial session for this course and of this session. And this session belongs to the last week's content, that is week number 12. Okay, and the theme of this session's discussion is again combustion and flames. So we will be continuing with the discussion that has been done in the previous week, right? And the instructor for the course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati, and I'm Aditya Sharma, again from Department of Mechanical Engineering, IIT Guwahati. I'm a research scholar here. So we shall start in another few minutes. Let's wait for a couple of minutes and then we can start with today's session. Thank you. So I believe we can start with the session. So as I've already told, the theme of this session again is combustion and flames. So basically, there are two lectures in this week 12's content. First discussion in the first lecture revolves around the evaporation of droplet that we see in a non-premixed combustion system. And after that, the lecture number 32, that is the second lecture of this week. In it, discussion is there on different engines. Engines, namely a petrol engine, diesel engine, then gas turbine engines, and then rocket engines. Okay, so briefly, one by one, we will see the topics. So the session will go this way. First of all, we will briefly uh, revise the topics that have been covered in week 12. After that, we will be seeing some theoretical questions or conceptual questions. And in the next section, we will be seeing the numerical type of questions. Okay, so let's start with the topics first. Okay, so this is lecture number 31. Here, your first heading is droplet evaporation. So, as I have already told that discussion in this lecture will be on non-premixed combustion system. I hope you all remember what is a non-premixed combustion system. Basically, one where the fuel and oxidizer are not pre-mixed, okay, before combustion. So, in this type of combustion, when the fuel and oxidizer diffuse, this gives rise to combustion. So, this is how we differentiate this type of combustion system from a pre-mixed combustion system. Okay. So this is one thing about it. So in this droplet evaporation, first we are seeing the mass transfer. So mass transfer basically is we have droplet of a fuel. Okay, it gets heat from the surrounding, right? Maybe initially in the form of some spark, and after that some portion from the surface of this droplet starts evaporating. So the transfer of this mass from this droplet towards the surrounding. Okay. So to have a detailed knowledge of this is important to understand the combustion in detail. Okay. When such type of combustion is taking place. So discussion has been done keeping this aspect in mind. Correct? Okay. Then what we see here is we are introduced to a law, that is d square law, right? Which numerically is this. Now what is d here? D is the diameter of the fuel droplet at some time t. Okay, t is time. Your d naught is initial diameter of the droplet, right? And then your k is evaporation constant. Okay, so this is the main thing in this topic, right? Droplet evaporation, mass transfer. Then your next topic is evaporation rate, evaporation rate, mass transfer. So this d square law comes under this only. Okay. So your d square law is under evaporation rate only topic. So these two topics we have covered. Now the third topic is droplet evaporation heat transfer. So this was about mass transfer. Then is when the your drop receives heat. So how do we analyze that? Okay. So this has been done in this topic. And from here we get two formula. This is droplet evaporation mass transfer. Then is heat transfer. So here we have first is your evaporation rate. There are two formulas in this topic, right? Evaporation rate is given by this formula. This is Ln is natural log. Now here your kg is thermal conductivity. Your RS is radius of droplet. Okay. Also liquid vapor interface radius. Then is BQ. BQ is basically transfer number. So I'll write an expression for transfer number also. And here CPG is gas phase specific heat. Okay, so these are the things in your evaporation rate expression. Then what is your expression for transfer number? That is BQ. CPG know we know what is. Then here this is okay. Now T infinity is temperature far field. Okay. T boil is boiling temperature of this liquid droplet. Okay. Then is your this enthalpy HFG. Okay. Which B is the standard meaning. For F is for your fluid and G is for your gas, right? So this is your BQ, right? Then also we have droplet lifetime, expression for droplet lifetime. This is D naught square by KQ, where KQ is evaporation constant and D naught is the initial diameter of the droplet. Correct. After that, next heading is droplet burning. So in this droplet burning topic, the expressions that will be of help to us is first fuel droplet mass burning rate, okay, which is 4 pi kg rs. So this we have already written, but again I'm writing this, okay. Right. Then one more expression for transfer number B naught Q is, so what is K subscript G? We know, right? This we know. And what R subscript S is, we know. What is C subscript PG, we know. Okay. Then this is the expression. So this is it. And for again, next is your flame temperature. Okay, that is, then is TF. Just tell the nomenclature that has been used here. So here QIL is what? Heat conducted into the interior of the droplet. So when we in this uh, discussion on droplet evaporation, uh, heat transfer. So the model we are using for our discussion in this, we assume that there is no heat that penetrates into the interior of the droplet, and the heat that we are receiving, all that heat is being used to convert your droplet, the surface of the droplet into vapors. Okay. So in that case, this thing becomes zero. In such, in case of such an assumption, right? So this is it. Then HFG we know. What is mu? This is basically air to fuel ratio. Okay, stoichiometric. Correct. And everything else. Okay, and also what is delta HC? What is this? This is specific enthalpy of combustion. So these are the expressions that have come in the discussion of this topic, okay? And these will be of use to us to solve our problems. Okay. Now after this, we have the next lecture, that is lecture number 32. Okay. Just give me a second. Okay. So then we have lecture number 32. In this lecture, the discussion revolves around different engines, okay, and how the droplet evaporation takes place in these types of engines. First is this. After that, the next section of this lecture is on the emissions, okay, from the products of combustion that are undesirable, okay, and that pollute our environment. So let's see these. So first is your combustion in petrol engines. So in the combustion that takes place in petrol engines, this combustion process is divided into three regions. Okay, first is your ignition and flame development. Second is your flame propagation. is your flame termination. So out of these three regions, the second one, that is flame propagation, the maximum burning of the fuel takes place in this region only. Okay. After this topic, we have combustion in diesel engines. So in petrol engine, this is premixed air fuel mixture is used. Okay. But in these, droplet burning comes into picture. Okay. Droplet burning, which is a part of non-premixed combustion system. Correct. So in it, first is your diesel engine. So diesel engine primarily has two types. Okay, this is your diesel engine. First is indirect injection. Second is direct injection. So in it, fuel is injected to pre-combustion chamber. Here, through multi-hole injector. Okay. So what happens if we see the combustion? Firstly, when the fuel is injected in the combustion chamber, it gets pre-mixed. Okay. And this burning is same as in the pre-mixed type of combustion system. But what happens is that once we have a flame and we again inject the fuel in the combustion chamber, in that case, the combustion that takes place is of diffusion type. Okay. where the fuel and oxidizer, when come together, diffuse, they give rise to further combustion. Okay, so firstly, premixed type, diffusion type afterwards. Okay, so this is how the combustion takes place in diesel engines. Then the third is your gas turbine engines. So what happens in gas turbine engines? First point is that there are three zones, okay, that have been divided in a gas turbine where the combustion takes place. Three zones, namely primary, secondary, and then third is dilution, dilution zone. Okay. So how the combustion is achieved here? So fuel is atomized, okay, and afterwards the combustion is initiated, okay, of the fuel. First the fuel will be injected and then it will be atomized, okay. After that you get a flame out of combustion. All right. So we were discussing the combustion in gas turbines, and I had a poor internet connection because of which I got disconnected. Sorry for that. So I was explaining this, that we have three combustion zones in a gas turbine. Okay, primary, secondary, and dilution. One important thing in these gas turbines is that when the combustion products exit the gas turbines, they are at very high temperature. Okay, so somehow this combustion products eventually will have to enter the turbine. Okay, to run the turbine, these will have to be used from the combustion chamber. But then these are at very high temperature, so this temperature has to be somehow regulated. Okay, so for that this dilution zone comes into picture. Okay, so this is the important of the dilution zone, correct? Okay, and in the primary and secondary zone you get to see the combustion in these two zones, correct? Okay. After this, we have next topic, that is combustion in rocket engines. So combustion in rocket engines. So rocket engines, as we know, are very important type of engines. So in it, basically, how the fuel and oxidizer is fed into the combustion chamber that divides the particular liquid rocket motor into two types. Okay, so combustion in two types. One is pressure fed, then another is pump fed. Okay. So these two types. In one type, as the name suggests, by means of pressure, the oxidizer and fuel are fed into the combustion chamber. And the second one is pump, where we use a turbo pump, okay, to have the fuel and oxidizers in the combustion chamber, right? So in this type of engine also, your oxidizer and fuels are injected, okay, in the combustion chamber to form droplets. And after that, the combustion of these droplets take place. Okay. So for your droplet combustion, we have seen how the droplet evaporation and the droplet burning takes place. So that type of analysis is also useful here. Correct. So this is your combustion in rocket engines. After that, we have discussion on the emissions. So different type of pollutants that are emitted in combustion and that are not desirable. This has been discussed. And out of all these, the depletion of ozone is one particular topic that is of great concern to us, right? So your depletion of ozone layer. So emissions from combustions are responsible for this. Okay. Then is your quantification of these emissions. So how do we quantify the emissions? So how do we do this? So there is emission index. There is one index that is EI, emission index. So this is used to quantify one of the measures to quantify the emissions. So for a particular species I, where this mole fraction of this species is compared with the carbon monoxide and carbon dioxide, and we get this measurement. Here X is your mole fraction. Okay. Then MW is your molecular weight. X is your number of moles of carbon in a mole of fuel. So this is one of the formula that is used to quantify the emissions. Okay. Then the last topic is on your turbulent flame. Sorry. So turbulent combustion, basically wherever you see turbulence, so predictability becomes very less. Okay. And to analyze such scenarios also becomes very difficult. So here, when we talk about turbulent flames, so there are three regimes in a turbulent flame. One is your laminar flame zone, then is your flamelets, eddies. Okay. Then last is your distributed reaction zone. So this has also been written in the slides, one of the slides, that there is no definite solution for a given application. Rather, empirical correlations are relied upon for realistic estimates. Okay, so this tells you that how challenging it can be to analyze scenarios where turbulence is there in picture. Okay, so these are the topics that have been covered in this week's content. Now we will move on to questions. So let's see the questions one by one. So first is this question. Please have a look at the question and see what's the correct answer to it. So your first question is on combustion in diesel engines, and it says that the first fuel injected into the chamber of diesel engine burns in a premixed flame while the fuels injected subsequently. Should have been fuel. So fuel injected subsequently burns in a diffusion mode. So about diesel engines, this is a correct statement. Okay. So we have seen that first we will inject some fuel, it will get premixed, and then the combustion will initiate. We will have a flame. After we have a flame, we again inject fuel. So this fuel we have in the form of droplets. Oxidizer we already have. These to diffuse. Flame we have, and the combustion takes place. And the droplet evaporation can be the analysis based on droplet evaporation can be taken help of in such scenarios. Okay, in such type of combustion. So this is a true statement. Okay. Then we will move on to the next question. Next is this question. So please see this question. Question is on evaporation rate, mass transfer. Mass transfer of your fuel droplet. So the question says that in the non-premixed combustion systems, non-premixed is diffusion-based combustion system. What is the nature of relation between d square and time, where d is the diameter of the droplet? So what is the relation? Let's check the topics that we have briefly discussed. Do we get some hint here, there? So if you see this, your d square law, the relation between d square and time t, what is the nature? The nature is linear. Okay, and yes, the slope here will be negative because we have negative sign with k, that is evaporation constant, but the relation clearly is linear, that is of line. So the correct answer to this question is option number A. So it's 4 p.m. already, and now we will take a short 5 minutes break, and after that we will continue with our session. Thank you. Okay, so let's continue with the session. So your next question is on quantification of emissions. So this is your question. Question number 3, and it states that the emission index EI for a pollutant species is the ratio of mass of the species to the mass of the fuel burned by the combustion process. So the question is on emission index. And this is one of the definitions of your emission index. So I have written one formula for emission index, and this one is also the correct form of emission index. Okay, so in that case, this is a true statement. Question number 4 now. We will see question number 4. This was question number 3. So the question number 4 is on evaporation rate mass transfer, and it states that the droplet lifetime in non-remixed combustion systems depend on dash and dash. What and what? So please see the options and try to see what the right option will be. First of all, what a droplet lifetime is. The droplet lifetime basically is the time taken by one droplet to completely evaporate. Okay. So when will that happen? When the diameter of the droplet will come down to zero. Correct? So, sorry. So how do we? So this is your expression for droplet diameter and then with respect to time. So what you see here is that though I have a direct expression for droplet lifetime, but this can be easily derived, right? You see your question number 4. This is your d square equals to d naught minus kt. So at droplet lifetime, d will be equal to 0. Life 0 equals to d naught minus kt. In that case, n equals to, sorry, so it will not be like this. It cannot be derived like this. I was wrong. It cannot be derived like this. No. Okay, I was writing the expression wrong. So d square is d naught square minus kt. It is like this. So this will become 0 and this will become kt. Then your t becomes d naught square by. So this is your expression for droplet lifetime. Okay. So if you see this, first is your initial droplet diameter and then is your evaporation constant. These two parameters are needed. So here in the four options, if you see, C option, if you see, the initial droplet diameter and the evaporation constant. This is the correct option that will be the answer to this question. Okay. So this way it can be done. Right. Now moving on to next question. The question is on again droplet evaporation mass transfer. It's a true or false type of question. Question number 5, which states that in a non-premixed combustion system, that is diffusion type of combustion system, where the combustion takes place in the diffusion of fertilizer and your fuel. With increase in transfer number, the evaporation rate decreases. Now, to answer this question, we need to know the relation between the transfer number and evaporation rate. So, what is that relation? So, for this, there is one expression, okay? And the expression is this way. So, this was question number 5. K equals to 8 rho DAB. Your rho is density, DAB is your diffusion constant, binary diffusion coefficient. Okay. And your B subscript Y is nothing but transfer number. Rho is your overall density and rho L is your liquid phase density. So now if you see the relation between your transfer number and your evaporation constant, so clearly this is a direct relation. Okay. So if your evaporation constant increases, then your transfer number also increases. So your this transfer number is the basically the driving force for your evaporation. Okay. So as your transfer number increases, the evaporation rate also increases. Okay. So if your transfer rate will increase, your evaporation rate will also increase. So this is a false statement because opposite statement has been given. So B option is correct in that case. Okay. So moving on to the next question, which is question number 6. So let's see question number 6. This is on droplet evaporation heat transfer. And it is a fill in the blank type of question. So please have a look at this question and try to see what the correct option will be for this question. So the question number 6 states that the Lewis number, that is the ratio of thermal diffusivity to the diffusion constant, is assumed to be dash for a droplet evaporating in hot gas in a non-premixed combustion system. Okay, so Lewis number has been talked about and its definition has also been given. So this is a ratio of thermal diffusivity to the diffusion coefficient. Is assumed to be dash. Options are given 0, 0.5, 1, 2. So so when we had discussion on droplet evaporation heat transfer in the lectures, there it has been given this that to analyze our droplet evaporation, we make some assumptions, okay, to simplify the analysis. And this is one assumption in that. And the assumption for Lewis number is that, but this ratio is unity. This ratio is 1. Okay. For our discussion purpose, we have assumed that it is 1. So in that case, option C is the correct option in this question. Okay. So all such type of assumptions we do to simplify the study, okay, that we are undertaking to better understand the droplet evaporation in terms of heat transfer, right? Okay. So this was your question number 6 on Lewis number from droplet evaporation heat transfer. Lecture number 31. Okay. So then this was answer C. So moving on to next question. Question number 7 on droplet burning. So please see the question. And let's see what will be the correct option to this question. So the question here is, the fuel vapor mass fraction is maximum at the dash and it decreases monotonically to 0 at the dash where the fuel is fully consumed. So this is from the non-premixed combustion system context. So your fuel vapor mass fraction is maximum at what location and it is 0 at what location. 4 options have been given. So whether it will be maximum at droplet surface or flame, and whether it will be 0 at flame or at far field or at droplet surface. So what will be the correct answer to this question? So out of these four options, the maximum mass fraction in droplet evaporation and burning in case of a non-premixed combustion system is at the droplet surface. Okay, and so there are zones. So there is one zone between your droplet surface and flame, that is the inner zone, and then there is one zone between your flame and your far field, that is the outer zone. Okay, from your outer zone you get the oxidizer, and from your inner zone you get the fuel. So when you see the flame, the mass fraction of the fuel is minimum at the flame. Okay, and it is maximum at the droplet surface. So seeing the options, option A is the correct option, right? So if you see the answer, so A is the correct option. Okay. Then the next question is on combustion in petrol engines. This is question number 8. It states that maximum burning of a fuel in petrol engine occurs in which of the following regimes? So in petrol engine we have seen, if you see the topics discussed, this is your combustion in petrol engines. So there are zones. So I had mentioned that the maximum burning of the fuel takes place in your flame propagation. The second bullet point. So if you see the options here, which region? So flame propagation region is option number A. So this is the correct option. Okay, now moving on to, so A option is correct. Moving on to next question, that is question number 9. Based on combustion in rocket engines, so supersonic combustion takes place in dash engines. So this has been taken from this topic. So combustion can take place in supersonic conditions, and when the flow is supersonic inside the combustion chamber, and it also combustion generally takes place with subsonic flow inside the combustion chamber. So in subsonic conditions and certainly the supersonic. So the question here asks that the supersonic combustion takes place in dash type of engines, dash engines. Four options have been given. One is your turbojet engine, then is your turbofan engine, then is your ramjet engine, then is your scramjet engine. So out of these, which one is the correct option? So in all the first three options, your combustion is subsonic. And your last option, that is your scramjet engines. So scramjet engine basically is supersonic ramjet. Okay. So in these type of in this type of engines or in these engines, the combustion that takes place in the combustion chamber is in supersonic conditions. Okay. D is the correct answer to this question. Then moving on to next question, based on pollutant emissions. So the question says that, please read the question. Which of the following is responsible for the depletion of ozone layer? So if you have gone through the lectures, you will know that for ozone depletion, these equations are responsible. Okay. First, this breaks the NO breaks the ozone into this, and then we have, when you have your NO2 with this single ozone, single oxygen, this reaction gives to again N. Okay, and this continues, which leads to depletion of ozone. So if you see the options, your option B is the correct. So B option is correct, NO. Then we have question number 11, which is on droplet evaporation heat transfer. And it states that in a non-premixed combustion system, the derivative of square of droplet diameter of fuel with respect to time, that is this, is function of mass, function of density, a function of surface temperature of the droplet, or constant. So question number 11. Solution. Your d square law. What does it states? Differentiate with respect to time. Zero minus k dt by dt d by dt of t. So this will be minus of k. So k is your evaporation constant. Clearly this is a constant. So the correct option will be B option, right? So let's see the answer. So B is the correct answer. So now moving on to the next question. Droplet burning. So this is question number 12. It states that in a droplet burning in a non-remix combustion system, the concentration of combustion products is maximum at which of the following? So the concentration of previously the concentration of mass fraction of fuel was asked, right? Here the concentration of combustion products has been asked. It will be maximum at what location? So four options have been given. Whether droplet surface, droplets interior part or inner core, it will be at the flame or somewhere in the far field. Correct option to this question is C option. It's the flame sheet where the concentration of combustion products will be maximum. Okay, so C is the option. Okay, so now moving on to so now we will be seeing the numerical questions. This is the first numerical question, question number 13. It says that a spherical fuel droplet with its initial diameter of 0.23 mm evaporates in a combustion medium by assuming d square law. If evaporation constant is this, then the lifetime of fluid droplet is. So we know lifetime. How do we calculate that? Lifetime is d naught square by k. D naught here is 0.23 mm. Seven. Let's see the question again. Okay. In SI units. So now if you solve this, this will come out to be solve this, this will come out to be 0.078 seconds. Okay. So this is question number 13. Let's check the answer. So this is 0.078. Okay. Then is your next question. Question number 14. It states that this is on quantification of emissions. So in an engine test with butane as a fuel, exhaust gas is found composed of carbon dioxide, carbon is this, oxygen is this, nitrogen oxide is this. Okay. So this should have been carbon monoxide CO. It should have been CO here. Okay. Carbon monoxide. So carbon dioxide, carbon monoxide, oxygen, NO, and then methane equivalent equals to 135 parts per million. So this has been given. Now the emission index of unburned hydrocarbons expressed equivalent to methane is. So we have to find it equivalent to methane. Okay, let's do this. So your mole fraction of CO2 is 10.4%. That is this. Of your carbon monoxide is 0.0008. Okay, because this is 0.08, right? So you divide it by 100. Then for oxygen, this is 0.0175. Yes. Then for NO it is 46 parts per million, which is this. For methane it is 135 parts per million. Okay. Now molecular weight of CH4 is 12 into 1 plus 4 into 1, which is 16. Molecular weight of butane is 58. And X is, for butane it is number of moles of carbon. It is 4. Okay. So your emission index in that case will be this. So if you put the values, this will be 0.00133 kg per kg of fuel. And in grams, if you see, this will be 1.33 grams per kg of fuel. So this is the answer. Okay, 1.33. Now moving on to next question. So these are 3 questions based on this information, which is as follows. The information is to consider the combustion of an hexane droplet, which is C6H14. When its diameter is this, the enthalpy of combustion is this, thermal conductivity is this, surrounding and the boiling temperature are these 98 Kelvin and 345 Kelvin. Okay, so this information has been given. First is your mass burning rate in kg per second. So for this, what we will do is, okay. So first of all, okay. Solution. So D naught is given as okay. Then radius at the surface of the droplet becomes half this. Then your enthalpy of combustion is kilojoule per kg. Then your thermal conductivity is then your temperature of surrounding, temperature at surface, that is boiling temperature, is then your gas phase specific heat is 3.56 millijoule per kg Kelvin. Then your HFG is 241 kilojoule per kg. Molecular weight of fuel is molecular weight of C6H14 hexane. 6 into 12 plus 14 into 1. This comes out to be 86 kg per kilogram. Now molecular weight of air is kg per kilogram. Okay. Now after this, the mass burning rate. What is this? This is 4 pi kg Rs, this we know. Cpg, this we know. Ln 1 plus P naught Q. Now B naught Q we don't know, that is transfer number. and V naught Q we know is delta H C by plus now here if you see we don't know this thing which is air to fuel ratio stoichiometric. Okay, if we know this we can know the transfer number. Now to know this we need to balance the equation Cxhy plus AO2 plus 3.76 N2 gives rise to HCO2 plus Y by 2 H2O plus 3.76 AN2. This. Now the air fuel ratio is 4.76 A molecular weight of air divided by molecular weight of fuel, and A is x plus y by 4 equals to 6 plus 14 by 4 equals to 9.5. So the air to fuel ratio comes out to be 4.76 into 9.5 into 29 divided by 86. So if you work this out, this will be 15.24. Now burning rate will be no. Still we are left with transfer number. So this will be, if you use the values in the formula given above, put the values in the formula given above, and this will come out to be this. Now we can put all the values that we have derived in the formula given above, and into ln of 1 plus 10.99. So if you solve this, this will come out to be okay. So burning rate formula has been used from here. Okay. Kg we knew, K subscript G we knew, RS we knew, V naught comma Q we found out, then CPG we knew. So this way we solved this, right? For V naught Q we needed air to fuel ratio. We found out the air to fuel ratio first, and then we did this. Now question number, next question. This is question number 16. The flame temperature in Kelvin is. So now we need to find the flame temperature. Okay. This is question number 16. So flame temperature equals to QIL plus HFG divided by CPG1 plus this. Then, so all these values we know. We just have to put the values here and get our answer. So this is into 15.24 into 10.99 minus 1 3.56 into 1 plus 15.24 plus 345. So when we work this out, this comes out to be 1039.005 kilogram. Okay, so this is the answer. Question number 16. Now question number 17, the ratio of flame radius to droplet radius is flame radius to droplet radius. What is the ratio? Let's see. What is this ratio? Question numbers. So this flame radius to droplet radius. So this has a formula, natural log 1 plus q divided by natural log divided by this. Okay. Now if we put the values and work this out, this will come out to be 39.0. So you can this way solve this. All right. So this was question number 17. Okay. So now we are at the end of this session. We have completed all the questions that were in the session that were planned for this session. So I'll conclude now this session. So this session was on combustion and flames, where there were two lectures. First lecture was on your droplet evaporation that we see in the combustion systems where diffusion is in picture. Okay. Then how this droplet evaporates, the mass transfer related to this evaporation and the heat transfer in this droplet evaporation, and how the burning of this droplet takes place, and what are different regions in this burning. All this has been covered in the lecture number 31. And in the next lecture, that is the last lecture of this course also, uh, first of all, different engines have been discussed. Okay, first was petrol engine where premixed combustion basically is in picture. But then after that, we saw diesel engines, rocket engine, and your gas turbine engines where your droplet evaporation uh, is in picture. Okay, so this discussion was done, and after that there was a discussion on the emissions from the combustion. Okay, and what are the impacts of these emissions and how can we quantify these emissions? So one such quantification was emission index. One such parameter to quantify the emission was emission index. And at last also we briefly saw what a turbulent flame is. Okay. So based on these topics, we did 12 conceptual questions and theoretical questions, and then we did 5 numerical questions based on these topics. And this way we completed our today's session. So I'll say goodbye at this point of the session. And as far as the questions are concerned, this is the last session. Okay. But then there is one more session we have organized that will be that we have called as a course concluding session. In this course, I'll be briefly discussing all the topics that we have covered from lecture 1 to lecture uh, week 1 to week 12. Okay. So this session will take place on coming Tuesday. The timing for the session will be 10 a.m. to 12 p.m. So hope to see you guys in that session. And this is for it today. And happy learning. Thank you.